Summit here in Denver, Colorado. Another exciting day. Yesterday was all about the future of energy technology. Today, it's about the future workforce that will drive that future. You know, one of the great things at ARPA-E is they've always had a great student component to the conference. I'm joined by Magee, who leads our recruiting. Megan, tell us more about this student program that they have and how GE is involved.
Yeah, great. So I'm super excited to be here. Again, ARPA-E has been a great partner of ours from the student aspect. So for the past 2 days, we participated in a career panel where we were able to provide insight to students about industrial research, advice on careers, hopefully coming to work for GE Research. Today we spent time doing a networking event with other companies, other academia, and we just recently finished up with a GE Research session where we had a number of graduate students with PhD and masters come to network with a bunch of GE Research technologists and looking for positions at GE Research, and we're super excited at the potential and hopefully being able to employ these great students at GE Research as part of industrial research and really bringing research to reality.
I gotta tell you, meeting some of the students, you know the future is in good hands for sure, and hopefully some of them will come to work for GE Research.
That's right.
Thank you, Megan. And let's now go to our next 3 videos, our ARPA-E in 3.
Hi, I'm Sayan. I'm Senior Engineer in Probabilistic Design and Optimization at GE Research. We are working in building a machine learning framework for inverse design. The idea is how do we reduce the cost and time for any kind of energy system by reducing the number of iterations we go through in design optimization process. So with this inverse design, explicit inverse design, what happens is you, as a design engineers, you provide the targets and you get the solutions immediately. So you don't have to go through any iterations. So one of the bigger challenges for these problems are that you have to train this machine learning with a lot of data. And this framework, which we are developing, help us to reduce the overall number of data requirements and basically help in training this machine learning algorithm in a much more efficient way. And what we have done is demonstrated that on last stage blade of gas turbine, which involves aerodynamic analysis, structural analysis, aeromechanics systems. And what we have found that we are able to reduce the overall design cycle time and engineering labor cost by 30 to 50%, and also help in exploring space with better efficient design as well. So our goal is this technology can be applicable for any other domain, and as well as try to come up with new learning curve about any new applications or any new design. So with framework like this, we will be able to reduce overall design cycle time and labor cost by around 30 to 50%. And in addition to that, we can also improve the efficiency and performance of those designs by exploring more design space in a much more efficient manner.
Hello, my name is Reza Ghandi. I'm principal scientist at the Semiconductor group. So here we are very excited to have a booth on our program in ARPA-E Summit. This is based on silicon carbide superjunction technology, and we are in the 3rd year of the program. The target here is to develop silicon carbide devices targeting for 6.5 kV diodes and MOSFETs. This is the next generation of silicon carbide, so we plan to be building from the current silicon carbide technology right now that developed at GRC throughout this last decade, and we are pushing it forward, targeting much higher voltage with much lower loss, and enabling to go to higher frequencies switching, specifically for grid technologies. So now this will be enable new renewable technology to be added to the current grid, and also develop new technologies for future of the power conversion.
Hi, I'm David Smith. I'm a principal scientist at GE Research. So we're working on a gas discharge tube circuit breaker to enable medium voltage DC, MVDC transmission. These are really critical for incoming renewables integration into the grid. If you look here, you can see a mock-up of our device. So the critical features are we've got an anode, which is shown by this red material, and a control grid, which is the blue. and that's set up in a way to allow us to have a large standoff voltage, so that when we want to interrupt the current, then we can actually stand off up to about 100 kV. We also want to be able to conduct high current, and for that we've got a cathode here, which is going to operate as a thermionic cathode, so you heat it up to get high current density. It's got potential for very long life, and those are kind of the key features of our device to enable this circuit breaker.